may have heard of one type of quantum sensor in the past. Atomic clocks have been around for many, many decades now, and they are sensors for time. So you leverage the intrinsic properties of a single atom to do some sort of timekeeping. Today, I will be talking about a new class of atomic sensors that is being used to detect AC electric fields. So your things like your Wi-Fi, your Bluetooth, your FM and AM radio, GPS, that sort of thing. So with that in mind, let's think about what is the difference between classical versus quantum sensing. In a classical sensor, this is a classical RF receiver, as we in the biz call it. You might call it an antenna, but it's basically just a chunk of metal that a field comes in, creates a voltage over either end of the antenna, and you read that out on the other side. A quantum sensor, on the other hand, says, well, okay, these fields that we're trying to sense are made of individual photons. What if we could measure what happens when those individual photons interact with individual atoms rather than an entire extended object in space? Why would we do this? Well, there are some impracticalities to a lot of versions of classical antennas. First and foremost is they can be a lot of times quite physically large. Typically, you'll need an antenna that's about the size of the wavelength of what you're trying to measure, which for a lot of radio stuff and radio telescopes like this one is really, really big, and it takes a lot to build one of those. The other thing is that they're kind of specific to their purpose. So a typical cell tower like this might have tons and tons of antennas on it, each one designed for a very specific band. Quantum sensors have a lot of capabilities that break these rules. So those physical geometry constraints, they're gone. You can get very broadband operation all the way down from DC, essentially, just a static electric field, all the way up to terahertz and terahertz. And another note is that they don't actually distort the electric field like a big chunk of metal will. So if you want to do another measurement nearby, it's completely sort of unimpeded by your sensor. So just get the basics of atomic physics out of the way. This is how these things work. So fundamentally, atoms are arranged into discrete energy levels. So as opposed to like in our macroscopic world, I can have my phone and it can be anywhere from here to here, anywhere in between. Whereas in atomic physics, it could only be here or here. And when I drop it, it gives off energy, and that is in the form of a photon. And you can also run the process in reverse. If you fire a photon at an atom, you can move it from a lower energy to a higher energy. But it does have to be just about the right wavelength between those two. So the color, essentially, of the photon corresponds to how far apart those energy levels are. An example that you would all be familiar with is a light-emitting diode, an LED. The physics of LEDs is a little more complicated, but the basic physics is there, where you have an electron that moves from a higher to a lower energy with a specific distance between them, and that distance is the color of your LED. So you might have a red LED. Blue LEDs were a big deal about 10 years ago. So in terms of modeling the atomic physics, we start with this guy, which is the Schrodinger equation. This is just a relatively straightforward differential equation. It looks a little bit complicated, but it's basically just matrix multiplication between that H, which is a Hamiltonian, which is a matrix describing the energy of the system, and rho, which is basically your X. That's how many of your atoms are in each state. And that's ultimately what we want to solve for, just like any other differential equation. And then the brackets are called a commutator. It's basically H times P minus P times H. And a Hamiltonian might look something like this for a relatively simple system. But that's okay for just a single quantum system existing on its own, but what if it's interacting with the real world and it's dissipating energy? Well, we add this other term, which looks a lot scarier than it actually is. This is essentially a single matrix. All these gamma terms are just a single matrix written out this way for generality, but in practice, at least in the way we do it, this is just one matrix. So we don't necessarily need to sum over all these n and m's, and this might look something like this. So let's build a quantum sensor. We're going to start with a cell of my favorite atom, which is going to be rubidium in this case, and I'm going to pick its two lowest energy levels, which I'll call 0 and 1. I'll shine a laser through it that is exactly the same energy as the distance between those two levels. And now, well, we also have a little bit of those dissipation that I talked about previously. So some atoms are just falling back down through natural processes. If I put a photodiode on the other side of the laser, I can measure what it looks like. And some of the atoms will be in state 0, some will be in state 1, but it'll be at a flat, steady state. Now I can add another level above it, and I can put a little RF horn that is exactly that frequency between them. And now the readout on my photodiode looks something like this. And we're doing quantum sensing now. A brief sidebar to talk about Rydberg states and why we like Rydberg atoms. If you think back to your chemistry class, you might remember these orbitals. These are just states. And one thing we really like about them is that the math for what all of their energies are is super well understood. And you can just crunch a bunch of numbers and you'll get the energy that all these things are. There's also a bunch of them, and they're really close together, and that makes them a really flexible platform for quantum sensors. So coming back to these equations that we looked at previously, we're going to call these the optical block equations, or OBEs. Deriving and typing these out for every experiment is cumbersome because the matrices that you're doing could be a whole bunch of different stuff. They get bigger and bigger the more and more levels your system has. So kind of the goal we want to do is automate this process. This is made more complicated when you have more complicated configurations like this one on the left, or these individual levels can actually turn out to be a whole bunch of levels. This is called fine or hyperfine splitting. So all of these things make it a lot more complicated. And historically, physicists haven't really had a great way to do this. There's also this issue that we're usually gonna sweep lasers over a whole bunch of different values for power or frequency. And all the atoms are moving around, which makes things even more complicated. So a new experiment might go something like this. You have a new grad student. They pick some tool they kind of know. And this is typically going to be an experimentalist who loves working with lasers in the labs and making cool stuff happen with lasers. So they pick something they sort of know, whether it's Python, MATLAB, Mathematica, and they kind of just slap something together. Maybe it takes them a few months. They write a paper about their experiment. It's awesome, but the code never sees the light of day. And this is a problem. It's not just an inefficient way to do stuff. It's just bad science because the code never goes out anywhere, and it's hard to reproduce the simulations, even if you can reproduce the experiment. So the goal of RydIQule is to fix this problem. A lot of physicists, especially in the lab, working with their hands a lot in the lab, have what I would describe as an adversarial relationship with computers. They use them when they have to, but they prefer to be on the optics table. And a lot of the ways they solve them are specific to their problem, they're using closed source tools, or they're just not written very well. They're kind of inefficient. So a good solution needs to address all of these, be general, be open source, and it needs to be fast enough that they can iterate in real time. So these are some very natural choices, at least to me, but not necessarily to your average experimental AMO physicist in the lab. We're going to use Python because it's straightforward. Jupyter, a lot of people are already used to Jupyter notebooks, and NumPy kind of takes that difficulty of actually writing efficient computation out of the way. So kind of the key insight that makes RydIQule so fun is that you look at this picture and you're like, well, I could write that as a graph. All of those levels could just be nodes, and all of the lasers between them could be edges. And you'll see pictures that look like that one on the left in optics labs all over the place. This is how every physicist is going to start their scratch work. And we can represent it as a graph just like that. So we kind of can meet physicists where they're already at, representing things in a way that they are already doing it without realizing it. Graphs help with generating the equations. We have the wonderful NetworkX package in Python, which we used to develop RydIQule. If you look at these matrices that I showed you before, this matrix gamma, this first one, can actually be thought of as an adjacency matrix if you construct it correctly. And these diagonal terms for the Hamiltonian on the bottom can actually be thought of as, you can use a shortest path algorithm in the assistance of constructing these, which makes scripting it a lot easier. You can have all sorts of the general, and any sort of graph you want. And then we can just plug those into our equation. And from the perspective of the hard part, right, the part that people aren't very good at doing, like we're done. We can throw this to any differential equation solver you want. The dictionary of dictionaries of NetworkX is also a very convenient data structure for us because you can add and remove stuff very easily, like laser power, laser frequency, whatever optional stuff you want. If you want to pulse the laser, It's super extensible because if people want to model systems that maybe we didn't think of and they have new parameters, they don't have to do anything extra. They just add a dictionary key to the graph. And we can pull atomic data from this wonderful library, ARC, which has kind of been the standard in atomic physics for fetching the properties of atoms. So the very last thing we need to do to help out these experimental AMO physicists is we need to use numpy correctly. So if you go to a lot of workstations in atomic physics labs, you'll find code that looks something like this, which, as I'm sure all of you know, this is not a very good way to go about things. You could be waiting hours or longer to wait for something like this to run because you have to call the Python interpreter at every single iteration of the loop. So we want to offload as much of this looping and the hard stuff out of Python as possible. And great news for us, numpy exists, as we just saw right before this. And numpy kind of handles all this broadcasting. So what RydIQule does is it looks at how many parameters you want to sweep over. Say you want to sweep over frequency and laser power for two different lasers, or maybe just one laser, or maybe you only want one of those things. You just look at how many of them are on the graph that are a list. You can reshape them to be easily broadcastable, and you can plug them into the exact same equations, the exact same code for generating the equations that you would have had if you just had a single number. And the fact that numpy is just plug and play like this has made our life so easy in the development of RydIQule. So now I'm going to open up a Jupyter notebook just so you can see exactly how easy RydIQule is. I'm not going to go into the physics here because it's more complicated than I can fit in a 25-minute talk, but the idea is there is physics going on, and hopefully you can see that there's physics going on, and there's not that many lines of code. So we start with our imports. We import RydIQule as RQ. It's nice that Q is, well, until a little bit more recently, a sort of underused letter, so we can kind of have our own, our own semi-unique two-letter abbreviation. And now let's look at this. We say what our atom is, rubidium-87. These are a couple of the laser parameters we're going to sweep. And then this is just, we define all of our states. So that's all of the levels in that system in that diagram that I showed earlier. We create our object, which is called a cell for RydIQule. So we tell it what atom we want, and we give it all the states, and it fetches all of this stuff from ARC and populates your graph with all of the physical parameters. And then you just tell it, okay, these are the lasers, so we're gonna go from state 1 to state 2. We're going to go from, state 0 to state 1 to state 2, state 2 to state 3 with these particular frequencies. And you can see we've just put in an array here, and we put in an array here. And then we add all those couplings to the graph. And we can see all of the info that we generate. We have this nice printout that tells you everything that's going on. You can see where all of the couplings, so the edges of the graph are, and all of the decoherent coupling. So all of those that natural falling down to lower energy states, that just gets added automatically. And you can see, we look at this stack of Hamiltonians, we call it a stack. We abbreviate it as stack of Ham early in the development, but it's a 4x4, it's a bunch of 4x4 matrices. So we have these 4x4 matrices, and these two dimensions are 301 by 5, which are exactly the dimensions of these. So all of those 4x4 matrices were generated all at once, and we have this big stack. And then all we have to do is call this function here. We get the solve steady state, we get the steady state solution, and then we can pull out susceptibility, which is a physical parameter that is basically what we see on the photodiode. And then we can plot it with matplotlib. It yells at us because I used LaTeX in the output generation. But this is a phenomenon called Otler-Town splitting, and you can see we've plotted over our 300 or whatever values of our laser frequency. Again, I'm not going to get too into the physics here, so I'm just trying to convince you that there is physics happening. And then as we iterate over this other laser frequency, we can see the splitting gets wider and wider and wider and wider. And that was all 10 lines of code. You could run this experiment and you would get out something that looked a little bit like this. Well, you'd have to spend probably a couple $1 million to get out your laser lab first, but if you already had a laser lab. So the takeaways here, what did we learn from RydIQule? Well, first of all, I think something that is a lot of times overlooked a little bit at a conference like this, where everybody that's coming here has some investment and interest in scientific Python, is that That's not the case for a lot of people. Sometimes people just want a piece of software that lets them code as little as possible. And outside of the space of really big, impressive fields, computationally impressive fields like your particle physics and your astronomy and your geosciences and stuff like that, where you just have terabytes and terabytes of data to sift through. A lot of physicists in the lab are slowed down a lot more by reinventing the same wheel over and over again than they are by actually executing their code. And that, that amounts to hundreds and hundreds of lab hours. And it's something to be mindful of, and the fact that we can create tools that help with that part too, using Python, and integrating with tools that we know work, like numpy and all these things that are built fast under the hood, is really helpful. It was not built for state-of-the-art speed. It has very good speed, because numpy kind of gives us that for free, as long as we set it up correctly. But it's built so that people who want to simulate the experiment that they're about to do can spend as little time as possible at their computer. And I don't think atomic physics is unique in this at all. All over physics, there's people who work in the lab doing experiments that they're there because they want to do the experiments. They're not there because they want to code. And they do incredible experiments, so tools like this can cut down their time spent coding, and it lets them do their experiments faster, and it accelerates science, because for them, the important part of their science is actually doing the experiments in the lab. So in a sense, this is a call to action, I guess, to maybe notice these things or point these things out and try to help in a way that you can. And it doesn't necessarily have to be a new super fast array reading mechanism or something super fast on the GPU. We have actually written RydIQule so that it is flexible and modular, and we're hoping to add a GPU backend at some point to solve the equations, because for big equations they can be quite slow. But the point is that we have solved a problem with relatively basic software engineering principles, and it has already saved, I know for a fact it has already saved probably hundreds of lab hours. So RydIQule has been pretty successful. We released it relatively recently, and it's being used. I just went on Google Scholar and I looked at some of our citations and just picked some of the institutions that people citing us were working at. There's a group I know for a fact at NIST that we've actually talked to before that's using it. So a couple companies, a couple university settings. And one kind of overlooked part about it is now there's a common language. This is phenomenal for reproducibility, right? You can just put in your paper, if RydIQule is more standard, you can say, we ran a RydIQule simulation, these were our parameters, and you don't have to say anything else, because RydIQule is there, and it's, I don't want to say it's a ground truth, because I'm not like gonna, stake my life on the fact that it's absolutely perfect, but if there's an error in that, it's an error in RydIQule that everybody can look at. And it really speeds up the communication and doing the actual science. This is another success that's very, very recent. We were contacted by a postdoc named Omar at University of Wisconsin-Madison, working in Thad Walker's lab. And he wrote this paper, like hot off the press, this was like 6 months ago, 6 or 8 months ago, that he had this cool analytic method to exactly solve over a single parameter dimension that we had. He wrote his specifically thinking about Doppler averaging, so all those particles moving around rather than solving for all of them independently. There's actually an analytic way to figure out exactly what the solution is. And he did a whole bunch of clever math to do that. And he contacted us. He was like, hey, I know about RydIQule, and I have this cool technique that I think can speed up RydIQule. Can I work with you on implementing it into RydIQule? And we did, and that's now up. It's on GitHub. For a lot of types of systems, it has reduce the speed that it takes to run, reduce the time, rather, that it takes to run stuff by a couple of orders of magnitude. So some things are running about 100 times faster when you don't actually have to simulate each individual slice. You can just do it once and say, do some clever linear algebra matrix inversion stuff, and you'll just get out the actual answer. We're still working with him on extending it to more and more parameters, and it's a really exciting collaboration. But it's already benefiting from kind of contributions from being open source, which I think is an amazing thing for the community. We have our source code hosted on GitHub. There's a QR code that'll take you there. It's through the University of Maryland Quantum Technology Center. We have a couple papers. We published our first one in the Journal of Computer Physics Communications, and we're now in review in JOS. That's RydIQule, and hopefully a little brief primer to quantum sensing. We have a QR code and GitHub link there, and I can take questions now.
Yeah, thank you very much, Ben. I really like the part, like drawing the similarities between computer science and like classic physics, like within representing these atomic status graphs. So we have a couple of questions. So the first one is by Gwen. So while I see the downsides, there may be educational benefits to reinventing the wheel. Have you found a way to still have that value in learning from grad students using RydIQule to learn how to build something from scratch themselves? Have you seen students contribute to new features, for example?
I think, so in general, in terms of what I've seen, I think the project is still gaining traction in the AMO community, and I think it's definitely not a de facto standard for grad students yet. I see what you mean about reinventing the wheel. I think we do provide access to a lot of the bare bones functions. I also think that the wheel that is being reinvented is not, I think it's not terribly complicated. It's not a complicated enough thing that I feel like people are missing out too much. Like ultimately, it's solving a differential equation that they have solved for homework problems, 20 times in the past. I think a lot of it comes down to the tedium of making sure your gigantic 15 by 15 matrix has all of the terms in exactly the right place. But I certainly see that there are downsides to having a tool like this. One thing I will say is that RydIQule we've tried our best to make it as accessible and amenable to things like plotting intermediate and seeing like the intermediate matrices and what exactly it's doing. You can visualize, we actually have a function built in that visualizes the actual graph structure that you've drawn. So I see that, but ultimately I think it's a relatively mundane thing that is mostly considered tedium by the people that do it. So it's mostly automating away the tedium rather than kind of replacing the understanding.
Okay, thank you. Next question is by Tetsuo Koyama. Was it common in your field to use network programming or networks? If you've primarily developed network programming from scratch, I'd be interested to hear what benefits you found in doing so.
I actually have no real experience in network programming in general, and with doing computations on graphs generally. This kind of was born out of RydIQule, and I was trying to come up with a way to compute what's called the rotating wave approximation reference frames, which is an approximation technique that's used. And I basically spent 3 days without realizing that I was trying to like rediscover graph math doing that. And I basically spent like 3 days trying to figure out how to write my own like crappy version of Dijkstra's pathfinding algorithm. And then I brought it to a coworker, and she's like, "That looks like a crappy version of Dijkstra's pathfinding." She said it nicer than that, but like that looks like a crappy version of Dijkstra's pathfinding algorithm. Have you considered just using Dijkstra's pathfinding algorithm? And then that led me down to find network X, and then we actually adopted the entire code from what we had before, which was a dictionary of dictionaries, and we're like, well, we can just replace all this with network X. And I don't think it's really done. That observation has been made before at all in the field. Like everybody that I've talked to. One thing I didn't touch on is that I'm not necessarily an AMO physics expert. I have a bachelor's degree in physics, and I've talked to a lot of AMO physicists, but I'm not an expert, so I don't know exactly what's standard in the field. But people that I've talked to have said, like, yeah, I've never seen this before, and that's really clever. People that are more expert in the field.
Okay, we have time for more questions. So the next one is by Nick Hartman. Any thoughts on how to add support for noise models?
I will say that I, at the moment, do not have a ton of thoughts. It is something that has been discussed, adding support for noise, because in the real world, receivers are noisy. We have discussed it, and we had some sort of very, very loose idea of how it might work, but I'm also not, like I said, I'm not an AMO physics expert. But it's something that has been discussed, but it hasn't been at the forefront of our development yet. It's one of the things that we're hoping to add in the future, maybe with the help of a summer student or a grad student or something like that.
Okay, yeah, one more question by Noah Stapp. How have the experimentalists reacted to using RydIQule at your lab so far? Has the adoption process been smooth?
Yeah, I think the reception, especially at our lab, at Army Research Lab, has been incredibly positive because it was initially developed basically to meet the needs of the researchers at Army Research Lab, and then it ultimately kind of grew into this bigger and bigger open source project. People that I've talked to, I suppose I haven't talked to anybody that's had a negative experience with it, but that might be selection bias. But people that have used it have basically said, like, we would write something like this in Mathematica. There's a Mathematica package called Atomic Density Matrix. And we would expect a simulation like this we would be waiting for a few days in Mathematica, and RydIQule solved it in 2 hours. So the general reception has been very, very positive, especially from people that I talk to regularly at my lab.
Okay, great. One last question. What's the goal moving forward with the project? Will the package be maintained or standardized in some way?
We are hoping to maintain it as much as possible. I don't know. The standardization is kind of interesting because there's not really a whole lot of packages like it that we need to interface with. But we're certainly hoping to maintain it, and Army Research Lab basically pays my salary as part of my job is to maintain it for the time being. And there are a few other people at Army Research Lab who know enough about it to help with that maintenance process. We are still looking to add new features. There's tons of cool analytical techniques, like I talked about with our collaboration with Omar, that can speed it up a ton. We have a steady state and time solver. Solving in the time domain is really, really slow for a whole bunch of technical reasons with the exact problem that we solve. But we're certain that this time solver can be sped up considerably. And there's a lot of cool analytical stuff in the realm of handling Doppler averaging, so all the particles moving around. So we're hoping to keep, development is definitely still active. It's not as active as it was about a year ago, but development is certainly still active, and we're looking to add new features to make it better. And talking to people at physics conferences that I was not able to go to this year for government reasons, is a big part of how we decide what we want to work on.